Thanks everyone for joining. I hope that we are no longer plagued by any Zoom connectivity problems. It's my great pleasure to moderate the second Twilight Talk organized by the Daylight Academy. I'm really excited about today's speaker with a very poetic title, How the Sun Paints the Sky. And as you'll discover, there's quite a lot of physics involved in that, underlying that poetic title. Before we get started, I just want to highlight what the Daylight Academy is. It's an international membership organization connecting scientists, architects, and other professionals with a strong interest in daylight and daylight-related topics. It encourages creativity and innovation through interdisciplinarity, and one of the goals is to disseminate knowledge among specialists and the public. And one of these dissemination mechanisms is this Twilight Talk webinar series. Now, this is obviously a webinar that you can participate in actively. And so if you want to ask questions, use the Q&A tool to write questions in the chat. The goal here is to basically, or the idea here is basically to write questions throughout the talk, and then we'll answer them after the talk as part of the dedicated Q&A session. So if there's something in the talk that you really want to get more information on, just use the Q&A tool, and then other people can actually comment and like these questions, and then we'll basically prioritize the ones that have received some, more community support, as it were. If you put questions in the chat, we will not be able to use them in the Q&A, so just make sure you use the Q&A feature. If you do write questions in the chat, I'll be there to say, please put in the Q&A. Now, without further ado, it's my great pleasure to introduce Bob Fosbury. He's currently an emeritus astronomer at the European Southern Observatory and an honorary professor at the Institute of Ophthalmology at UCL. He's worked for 26 years at the European Space Agency, working on the Hubble telescope and other telescope projects. And he's now spending his time in retirement trying to understand how the visual system of animals is optimized to capture information in the environment. It's my great pleasure to introduce Bob, and we're very excited to have you as part of this Twilight Talk series. Bob, the floor is all yours.
Okay, thank you very much. It's a great pleasure to have the opportunity to do this. I will delete my face and share my screen, and we can get started. So without further ado, I'll move to my first slide and start the story in the middle, more or less the middle of the 19th century, when the problem of the blue sky was beginning to occupy physicists who were at the time unable to explain why the sky was blue. That had been a documented problem for millennia. The Greeks, the Romans all wanted to find out why the sky was blue, but all had failed. And when William Turner painted this wonderful and very famous painting in 1838, nobody knew why the sky was blue, and therefore nobody really understood the range of colors that we see in the sky. Now, Turner painted this picture just 4 years before the birth of Lord Rayleigh, the third Baron Rayleigh, John Strutt, who in the end was the person who really understood the blue sky. There was a lot of activity both in the 18th century with Helmholtz and Saussure and people who were studying the sky very closely, but little progress had been made in understanding the physics. During the 19th century, people like Tyndall, Stokes, John Herschel, then Rayleigh, and eventually Einstein were all involved in this process. And it was in fact much more important than just the color of the sky. It was an attempt to verify the reality of molecules. And in fact, studies of the sky were important contributors to the determination of Avogadro's number in that period. So it was a very crucial part of physics. I have to say that Turner painted it wonderfully well, and I'll briefly overlay Turner's painting with a palette of colors that I've produced in my simple sky model. which I'll be describing during this talk. And you can see my colors are a little bit more saturated than the colors that Turner uses, but he's perfectly entitled to mix them. And in fact, physically, it is appropriate to mix them as well, because my model is very simplified. Now, 182 years after Turner painted this picture, we have the luxury of looking down on twilights from the space station. And I hope you appreciate my reference to 2001: A Space Odyssey, but I have a fish called Rayleigh's fish, which I actually have in front of me here, which is a very good model of the scattering in the sky. And you can see the distribution of colors in the twilight sky here, mirrored in Rayleigh's fish. And Rayleigh's fish is a scattering glass. It's a glass which scatters light, very much like Rayleigh scattering. It has metallic particles in it that are very, very small. They're not quite as small as the molecules that scatter the light in the sky, but they're good enough to produce a very good model. It was a hard struggle to understand all this. And I've done two things. I've got a little analog model here, which you can probably all play with. These are little cubes of what's called opalescent glass, which you can buy very easily in rock shops, in the high street, anywhere, if there are any left. And if you shine light on a surface behind them and look through them, you get these wonderful twilight colors, sunset colors. If you shine the light on them sideways and from your side, you get the wonderful sky blue colors. So they're very nice toys to play with. This is really Tyndall scattering rather than Rayleigh scattering. I'll come to that in a moment. It's the same process, but slightly different sized scattering particles. I've again computed a set of swatches for the colors that you see in that analog model, and you can see it's a pretty good match. So, what am I going to do in this talk? There's some of this talk which is critical for understanding what's going on. The first two items, the extinction, the color of the sun as it shines through the atmosphere, is crucial to understand. The scattering of the sunlight by the molecules and particulate matter in the sky is what actually paints the sky with the stolen sunbeams. That's where you get all the twilight colors from. I shall really try and explain that clearly so you understand that. The next element in the talk is, I call it the elephant in the room, you'll see why. It's the role of ozone in the colors of the sky. And this is not widely appreciated by many people. The fact that ozone is such an important gas, although it's not very abundant in the sky, it plays several extremely important roles. One of them is protecting us from ultraviolet radiation, but the other is making the blue color that we see at twilight, and I'll explain how that happens. When we've got that far, it doesn't really matter if we don't go too much further, although you'll miss some lovely pictures. So the remainder of the talk after that is a discussion of the effect of clouds, lunar eclipses, and really also the analogy with the kind of experiments we'll do to understand exoplanet atmospheres. And I want to explain what that analogy is so you can see why we're so interested in studying lunar eclipses. And then finally, there's a set of slides, basically. It's a short slideshow to show you what the sky can look like when it's dark, when it uses invisible radiation from the sun to pump it up during the day and release that light during night. And that's the air glow. Unfortunately, with our eyes, we can't see the colors clearly, but with modern digital cameras, we certainly can, and it's very spectacular. Now, why am I doing this? I'm, in fact, rather an inappropriate person to give this talk because I've spent most of my life trying to get above the atmosphere and avoid it. I have many colleagues, including myself sometimes on the ground, who try and look through it. Now, this is a wonderful picture of the Hubble Space Telescope being serviced in orbit, taken by Claude Nicollier, who's a great friend of ours, and he's a Swiss astronaut who's flown twice to Hubble on servicing missions on the space shuttle. And we asked him to take this picture for us, which he did in 1999. So this is Hubble flying above the northern Chilean coast in South America. And here we mark two of the major astronomical observatories on the planet at the moment. ALMA, which is a sub-millimeter radio telescope at 5,000 meters in the Altiplano, just south of the Bolivian border. Very spectacular place, not an easy place to work. In fact, people don't work there, they work much lower, remotely. And then we have the ESO Very Large Telescope, which is situated much closer to the coast at an altitude of about 2,800 meters, a little bit to the south. These are in the northern part of the Atacama Desert. The weather is extremely good. This cloud that you see over the Pacific rarely penetrates over the coast. There's an inversion layer there. So it's a wonderful place to observe. And so many of the pictures that I'll be showing you are taken at this site, this Very Large Telescope site in northern Chile. Now, I should explain to some of you, I'm sure not all of you, the nature of the visible spectrum, which is so important for understanding what's going on in the sky. So I'm just going to run through very quickly a picture of the spectrum. We have a plot here of the brightness of an object, the sky, say, in energy units, the vertical axis, and then we have the color or the wavelength along the horizontal axis. And you can see I've left this color patch in the background here, and I'll show you a few light sources which you'll be familiar with and show you what their spectra look like. The first one is the old-fashioned tungsten filament lamp, which emits very much like a black body. It emits most of its light in the near infrared where we can't see it. It's very wasteful. That's why we're using different kinds of light sources now. That's a typical LED lamp that you might have in your sitting room, which is restricted to the visible part of the spectrum and appears white. In fact, it appears what we call a warm white. You can get different kinds of LEDs. This is a sort of daylight LED, which is used a lot by photographers, where you get a stronger blue peak here and a weaker, longer wavelength emission. I have to say that these blue peaks here, which drive these LED emissions, are a disaster for wildlife, and they're completely unnecessary for humans. And we're trying to get rid of those from the environment and get much friendlier LED lights available in the environment. Get that animation. Okay, so I've introduced the spectrum. All I was going to show was the sensitivity of the human eye, but you'll have to take that for granted. Before we move on, I'd like to say a little bit about the Earth's sky and what it's been like during its 4.5 billion year history. Probably the first 2 billion years of the Earth's history, the sky was not at all like the one we see now. It wasn't clear, it wasn't blue. In fact, it was an organic oxide infested sky, which probably was a dirty orange color. And it was the first oxygen producing bacteria that began to appear early on that eventually produced oxygen in the ocean. And that oxygen eventually started filling up the atmosphere. And we end up about 2 to 2.5 billion years ago with the great oxidation event, which will have cleared the atmosphere by oxidizing all the nasty things in the atmosphere and clearing it up. So we've only had a blue sky really for the last 2 billion years of the Earth's history. And it's a very special blue sky because it has just the right thickness to give us a beautiful deep blue, but also enable the wonderful range of twilight colors. If it were less dense, if we had a smaller amount of atmosphere around the Earth, we would just see a very dark blue and we wouldn't have a chance to see the wonderful colors. If it were too much thicker, it would be a pale white, pasty blue, and also we wouldn't see the colors very clearly. So it's a very fortunate atmosphere for seeing the spectacular views that we do see. In the solar system, we can see atmospheres which are possibly rather similar to that. Titan's organic haze atmosphere, the largest satellite of Saturn, probably looks a bit like the early Earth's atmosphere, where we get this orange haze down at ground level. it's now cleared to produce this kind of picture we see from the space station, where if you look at the bottom here, we have the troposphere, where all the weather happens, where we get all the clouds and so on. We get the stratosphere here, which has the ozone in it. And in fact, I believe this dirty yellow band here is us seeing the ozone band in absorption. And then we get the very thin atmosphere above that produces very little effect for our visual sensations. So first of all, I'm going to talk about atmospheric extinction of sunlight. There are two processes involved in this, which I've labeled bold here, and there are three ingredients that go into the recipe. The two processes are the processes of bouncing incoming sunlight from the constituents of the atmosphere. Molecules on the one hand, this is mostly molecules of nitrogen, nitrogen-2, and oxygen, oxygen-2, and that produces the Rayleigh scattering, which is very strongly colored. Rayleigh scattering depends very strongly on the wavelength of light. It depends to the fourth power of the wavelength. So as you go to the blue, the scattering gets stronger very, very rapidly. It's about a factor of 10 stronger at the blue end of the spectrum than it is in the red end of our visible spectrum. And the other constituent that scatters light in the atmosphere, but is very variable in its content in the atmosphere, are the aerosols. These are tiny droplets of fluid, water and other things, and they're tiny dust particles. And for a typical aerosol content of an atmosphere in a normal kind of place, this still scatters blue light somewhat more strongly than red light, but it's a much weaker blue scattering. It's the wavelength to the power minus 1.3 rather than minus 4. So those are the scattering processes. There are also absorption processes. Scattering processes are where the light comes in, it interacts with something in the atmosphere, interacts with a molecule or a particle in the atmosphere, and it gets redistributed in direction. So it doesn't change energy, it remains the same color, but it comes off in a different direction. Occasionally, one of the constituents of the atmosphere will actually absorb light. So basically, it'll convert that light energy, it'll take it away from the light field that we see, and will convert it to something else. It might convert it into a photon of a different color, but it also might convert it to heat, which heats the atmosphere. And we call this absorption. And there are many different absorbers in the Earth's atmosphere, many of them very important, but most of them are at longer wavelengths, i.e. redder than our visible sensitivity. So most of them are in the near infrared and in the infrared, and we don't actually see them with our eyes. The only one that's really important in the visible spectrum is ozone. I've mentioned it before, it's our elephant in the room, and it is very important for visible light, but not usually during the daytime, just when the sun gets very low in the sky. So those are the processes that go into affecting the light that shines from the sun through the atmosphere to reach us on the ground. And we call that extinction. The light we see on the ground is not quite as bright as the light that an astronaut would see from space, because some of it's been scattered around the sky and some of it's been absorbed. It's also somewhat different in color because it scatters the blue light much more strongly than it scatters the red light. And I've got a little cartoon here. The few cartoons I have in this talk, actually, I didn't try and pretty them up at all. These were cartoons I drew on my iPad when I was designing this talk about 6 months ago, and I've left them as they were. So here you see the sun outside the atmosphere. It's shining down onto the Earth's atmosphere. Some of the light is getting scattered to make the blue sky. Some of the light is getting absorbed to make the light a different color. And if we're standing here looking up at the sky, we see a sun which is a little bit redder than the sun that the astronaut would see from space, because it's had a lot of the blue light scattered out of the beam. As you look lower and as the sun sinks lower and lower in the sky, you get more and more scattering, you get more and more absorption, and so this sun gets redder and redder as it approaches the sunset. Now, in the daytime, when the sun's high like this, the extinction is dominated by scattering. There's plenty of absorption going on in the infrared, but in the visible spectrum, we're dominated by scattering. And here I've got a spectrum, a somewhat detailed spectrum, but let me just describe what's on here. The thin grey line at the top is the spectrum of the sun outside the Earth's atmosphere. It extends well into the infrared on the right, and it extends into the ultraviolet on the left. You can see our visible spectrum here. Two things I want you to notice about this. This blue line here is the sunlight that would reach the ground with a modest altitude of sun, maybe the sun 40 degrees or so above the horizon. That's the light that would reach the ground. If you look at the ultraviolet end, you see the ultraviolet's gone. It's been absorbed by ozone gas in the atmosphere, and it's very fortunate that it has been absorbed because it would be very damaging to life. It breaks up DNA and does all kinds of nasty things. So this is one of the very important effects of ozone, is to get rid of the ultraviolet radiation. There's plenty of it in the sun. Some stars, hotter stars, of course, contain much more, but there's plenty of ultraviolet radiation in the sun. If we look redwards of the visible spectrum, we see these huge absorption dips. And these big ones are due to water in the atmosphere. They're very, very strong. Water is the main driver of global warming, of the greenhouse effect. But it's relatively constant in the atmosphere. CO2 doesn't appear as strong here, but it's much stronger in the further in the ultraviolet. And we have a few other absorbers here. There's no need for me to go into those, but you see methane and some oxygen, molecular oxygen, and so on. But in the visible part of the spectrum, we're relatively free of absorbers. The red lines here are measured spectra. I've measured these with devices that I have. I have them on my desk here. They're well calibrated, so I can plot them on this energy scale. So this represents what happens when we subject sunlight to extinction. And this is what you see when you look at the sun, which you won't do, of course, because it's too bright, but it's the light that is illuminating the landscape around you. Now, this is an important quantity to understand. It's called the optical depth. And I want to explain this by explaining, this is a column of air through the atmosphere. You can imagine this is 1 square centimetre in this square here, and we're extending this into a column which will extend many kilometres through the atmosphere. In fact, if you imagine this column vertically in the atmosphere, it will extend about 100 kilometres up through the atmosphere. But of course, the density of molecules in that long column will vary enormously from the upper atmosphere to the lower atmosphere. So we have a column of air with a variable density along here. And this column contains molecules, like nitrogen molecules or oxygen molecules. It also contains our aerosol dust particles, which are mostly just in the lower atmosphere, very few in the upper atmosphere, but it contains aerosols as well. And the way we characterize this column of air is by the density of scatterers in it, so the number of scatters per cubic centimetre, and I say this will vary with height. We characterize it by its path length, its linear path length, in which case we have to integrate this n through this long variable path length. But let's forget about that integration for the moment and just call it, we have the density times the length. And that produces something which we call the airmass, AM in this diagram, which is basically the number of molecules that we're looking through along this column that are able to scatter and have effects on the colors and the intensity we see. So the NL here is the amount of atmosphere in the column. And the sigma here is the strength of the scattering of the individual scatterers. And that's usually measured simply as a geometric cross-section measured in square centimeters. And this cross-section is applied both to the molecules, because they're very small for molecules, and for aerosol particles, which are somewhat bigger. So we have two things here. We have the strength of individual scatterers, and we have the total amount of atmosphere we're traveling through in this column. And you'll see the units here. We have centimeters to the -2 here and centimeters squared here. So when we form this quantity called the optical depth, which is just the product of these two, it's a dimensionless number. And we call that the optical depth. And just to give you some idea of what that means in terms of scale, an optical depth of 1 corresponds to the mean distance that a photon will travel through the atmosphere before it hits anything. Now, if we look directly upwards in the atmosphere, in the visible spectrum, that optical depth is significantly less than 1. So there's a relatively small probability of a photon hitting a scattering particle in its journey from the top of the atmosphere downwards, which is extremely fortunate for astronomers because it means we can look at the edge of the universe through our atmospheres. Otherwise, it would be very inconvenient if we were just looking at a misty haze above us. But it's still important, and it's still important for us to get above it. But so a tau equals 1, the optical depth we call the Greek tau, corresponds to this mean free path. And I'll give you now a few indicators of what different values of tau mean for us. The extinction, which produces the loss of light from the sunlight coming down through the atmosphere, the extinction is proportional to the negative exponential of the optical depth. It's the negative. I've called x here is actually the optical depth in this argument. So the extinction depends on e to the -x. Now, you have no excuse not understanding what an exponential is because you've heard almost nothing else through the COVID pandemic period, but that was a positive exponential. This is a negative exponential. So the light, if you have 1 unit of light outside the atmosphere, by the time you've got to an optical depth of 1, that 1 has decreased to about a little bit more than a third of what you started with. By the time you've got to an optical depth of 6, there's very little left. You can still see the sun through the atmosphere, probably with an optical depth even bigger than 10. But that's what the extinction does for you. So let me just skip the optical depth a bit. I think I've told you more or less what optical depth is. It's the mean free path of 1. If we look at a setting sun, which is a deep red color, that may be an optical depth of 6, 7, 8, 9, or 10, something like that. Now I've talked about extinction. I want to move on to discussing the sky now. I've got a plot here of, you've seen before, it's the sun outside the atmosphere, and I've got 2 spectra of the sun as it appears on the ground with modest altitudes of the sun. And then I've got 2 measured spectra here. One is the spectrum of a blue sky, which you see as extremely blue compared to either the sun or the extincted sun. And the other is the spectrum of an overcast sky, a quite heavily overcast sky, which is less blue, but still bluer than the sunlight coming down. Much of the missing light in the extinction has gone into making the blue sky. And so when you have a cloudy sky, the sky actually sees the sunlight coming down, and it also sees the blue sky. And so it mixes some of the blue sky back into what you see on the cloud. And this is why the cloud here is somewhat bluer than the extincted sunlight. I have to point out that these 2 observed spectra here of the cloud and the blue sky are, of course, very, very much fainter than the sun. I've had to scale them up by a factor of 150 here for the blue sky and a factor of over 2,000 for the cloud. But I'm talking mostly about color, so that's the important thing to take away from this. So the cloud actually is almost the same color as the sun outside the atmosphere. So when you're looking at a white cloud, you're looking at the color of the sun that would be seen by an astronaut, more or less. The other thing I just wanted to mention briefly here is that the clouds, and indeed the sky, don't just see the sun or the clouds, they also see the ground. And if the ground's covered in vegetation, you can see the reflection of the vegetation on the clouds very, very clearly. Because when we go a little bit above the red end of the spectrum that we can see, the leaves of the plants are extremely bright. And some of you will have noticed in infrared photographs that the vegetation looks extremely bright. It looks as bright as clouds in the sky and as bright as snow under some circumstances. And here in this spectrum, you can see these green areas here are the reflection of vegetation on the ground seen on the underside of a cloud. And actually, I did this experiment the other day. I was very surprised that actually you can see backscattering from a blue sky, which shows the chlorophyll in the leaves of the plants on the ground, even just looking at a blue sky. I found quite surprising. I hadn't realized that beforehand. The other thing we have to remember about daylight and nightlight is there's a huge dynamic range. There's a huge range in brightness from the brightest sunlit scene that we see, 120,000 of these units here. The lux unit, photometric units are a nightmare. I won't explain what they are in any detail, but a lux unit is a unit that's tailored to our visible spectrum range. So the spectra that I've been showing you show you real units in watts per square meter per nanometer or whatever. These lux units weight that number by the sensitivity curve of the human eye. So in daylight, we go a factor of about 100,000 or so down to the extremely thickest storm clouds seen at sunset and sunrise. So we've gone down by a factor of about 100,000 there. And when we go into nighttime, we go down by another factor of 10,000 or so. So that the darkest night you'll see where there's no moon and you have an overcast night sky is about 1 billion times fainter than we see in a bright sunlit scene, 9 orders of magnitude. And we see these scenes with our eyes. And I think this is a remarkable property of eyes, that it can cope with a dynamic range of 1 billion, not all at once. Your eye has to adapt to very faint lighting, of course, but you can see a huge range in dynamic range. Now let's get on to painting the sky. This starts from our understanding of extinction. And again, I've got a cartoon here, which shows the twilight colors here, the bands of twilight color we see as the sun sets. Now, the object is for us to understand how those colors are actually formed. Now, you see, I've put the sun in my cartoon here, close to the Earth. You've got to imagine this is a long way off in this direction. But this sun will shine onto the atmosphere. It can take a high route up here to illuminate the upper atmosphere above our heads, more or less. And it can be scattered from that down for us to observe. Or it can take a lower route in the lower atmosphere where there's lots more atmosphere. It can be scattered from down here to us. And then it will have traveled through a much longer distance, a much larger region of atmosphere. So we're going to explain how we get this band of twilight colors. I've already mentioned that the process of scattering these colors was a central topic in mid-19th century physics. I'm not saying anything about the polarization of light in the sky. You can have great fun by taking a sheet of Polaroid outside when there's a blue sky and twisting it around and seeing the light is highly polarized. I don't have time to go into that, but understanding that polarization was a very important factor of in the understanding of how and what was going on in the sky. So let's forget about polarization for the moment and just think about color. We have a slightly different diagram here where I've added a new factor into the equation. We had the extinction, which was just e to the minus tau. Here I've added in a source function. Now, what you have to imagine is you have to have the sun shining through the atmosphere towards you. It's also shining on the atmosphere elsewhere. If we imagine the sunlight shining on a patch of a volume of atmosphere somewhere in the sky and being scattered towards you, we can consider this volume of atmosphere as a new source of light. So it's like a new light bulb in the sky. And this is what's producing the light that you see in the sky, not in the sun, but in the sky. So when we try and understand the color and the intensity of light that we see in the sky in different parts of the sky, we have the first term here, which I'll call a source term. This is just the amount of scatterer in that particular volume of sky. It's proportional to the optical depth. But that light has to then travel towards you and be diminished by e to the minus tau. So we have two competing factors in this process, and they behave differently. This one is in the equation linearly, so the intensity just increases in proportional to the number of scattering particles we have, whereas the loss of light on the way to us decreases exponentially. And you've got to remember that this tau here strongly depends on the color. The scattering strength is much higher in the blue than it is in the red. So we've got this balance between a source and a sink. The source is the tau in front, and the sink is the e to the minus tau, and they're both varying with color. The light that we see at the end of this process is from near the peak of this curve, tau e to the minus tau. This curve peaks at 1, so it peaks at an optical depth of 1. And when we shine light into a turbid medium, the emergent scattered light that we see comes predominantly from this region where the optical depth equals 1. Now, this is a very important general principle, and it gives us a way of understanding how the colors vary in the sky. I might mention that we've also used this to understand the atmospheres of galaxies with quasars in the middle and so on. It's a very generally used technique for understanding what's going on. So let's move on to what really happens in the sky. So having explained that to you, let me imagine that you're standing somewhere on the ground down here, and you're looking up at the sky. These are two twilight skies from our observatories in Chile. This is on the left is a sunset sky. On the right is a sunrise sky. They're very similar. It doesn't really matter here. If we have sunlight shining high in the atmosphere, leaping up through the atmosphere and scattering from up here and traveling down to us, the observer here, it's traveled through a relatively small amount of atmosphere, the air mass that it's traveled through, because it's leapfrogged over most of the dense atmosphere. It's traveled high in the atmosphere. There's not so much air up there. In order to reach an optical depth of 1, we have to go to the blue, where the scattering strength is strong. So we've got small amounts of atmosphere, large amounts of scattering per particle. So we're balancing those two to make tau equals 1. If we take an intermediate path through the atmosphere, it's not going to let me do this again. I'm going to have to draw it by eye, but just imagine a similar track coming up through here, scattering off a parcel of air somewhat lower in the atmosphere and then traveling down to the observer. This balance of tau equals 1, because it's got more atmosphere, the wavelength will have to be longer where the scattering strength is weaker, and we can get a green in the atmosphere. And if we travel very low through the atmosphere and then scatter down here somewhere, down here, we've traveled through a very large amount of atmosphere, and so we have to move to the red where the scattering strength is very weak. And so this beautiful palette of colors between the deep blue in the zenith and the red and orange down near the horizon is the result of this balancing act between the the source of the light and the extinction of the light along this path to keep the optical depth equals 1. So I hope that's reasonably clear. I apologize that my jumping between slides is not working very well, but we can, I think, get rid of that. You can see it on you can see the curves on the direct view here. I'll just move on to the next. If you're watching one of these sunsets, you might take the trouble to look behind you. If it's a sunset and you're looking in the west, if you look in the east, you can see this beautiful phenomenon called the Earth shadow, or the dark segment. This is a shadow of the set sun. So the sun is set below the horizon, and so it's casting a shadow on the atmosphere. And in fact, it's more of a shadow of the ozone layer than it is a shadow of the limb of the Earth, in fact. And this deep color is really a reflection of the color of the sky above you at that time, of the zenith. It's rather like placing a sheet of paper towards the horizon and letting the zenith sky scatter off your sheet of white paper. It's a reflection of the zenith sky. And it's this beautiful, deep, metallic, purpley color, which, as I will shortly explain, is due to ozone. This I won't dwell on. This is just the model that I was using to produce those swatches of color that you've just seen. And what I'm doing here is I'm increasing the amount of atmosphere through this sequence of computed spectra in my model. So you start with a blue sky and you progress through a sort of greenish yellow sky to a red sky as you increase the total amount of atmosphere. And you might ask, what's this big dip doing in the middle, which I've used for this twilight model because it's really there in the twilight atmosphere. This is due to ozone absorption, and I'm just about to come to that. Before that, I just wanted to measure give an idea of what happens when you change aerosols. I've talked about Rayleigh scattering and mostly the effect of Rayleigh scattering on the atmosphere. If we have an aerosol-rich atmosphere, we get these lovely pastel sunsets, which I'm sure you've seen as a nice example. If we get peculiar aerosols, this is probably wind-blown dust in Arizona that produces this rather lurid range of colors at sunset. That's produced by aerosols. You often get this kind of color with volcanic dust after major volcanic eruptions on the Earth as well. But let's move on to ozone. Now, what does ozone do? Ozone is what we call trioxygen. It's a very unstable molecule produced relatively high in the atmosphere, between altitudes of about 12 and 40 kilometers in the atmosphere, by the effect of ultraviolet radiation on the oxygen molecular oxygen in the atmosphere. So it can break the two oxygen atoms in an oxygen molecule apart. And one of these can be captured using a catalytic process with other constituents of the atmosphere, can be captured into a trioxygen molecule, which is very unstable, and it can be broken down by ordinary orange and red light coming from the sun. And when that light is absorbed, it produces a very interesting absorption spectrum. And I show this absorption spectrum here. Let's try and understand what this plot is. It's the strength of absorption of ozone gas. This is the cross section. This is the geometrical cross section, which I've mentioned. Plotted up here in a logarithmic scale. And this is what happens over wavelength. This is the very, very strong absorption that absorbs the ultraviolet and protects us from ultraviolet damage. It's quite transparent in the blue, but in the orange and red, it has this extraordinary broad absorption band. The breadth and peculiar structure of this absorption band is due to the fact that the ozone is so unstable that when a red light photon hits the ozone, it makes it wobble like a jelly, and it'll last for about a millionth of a second before it breaks apart. And this very short time scale means that the absorption spectrum is very broad. So this broad Chapuis absorption here has an enormous effect on the sky. This is liquid ozone, which has this very characteristic blue color. It's a very different blue from the blue sky. If you're a painter, you'll use ultramarine for this because it's a slightly purpley blue. It has a red component as well. This is liquid ozone, which absorbs quite strongly, but it's the same absorption essentially that you see in the ozone gas in the atmosphere. Now, what happens at twilight is you have the sunlight shining in from the left here at sunset, grazing the atmosphere of the Earth. You get this shadow underneath, which doesn't see any of the light. And as the sunset proceeds, the upper atmosphere is being illuminated at higher and higher layers. And this diagram comes from a paper that was published by this American atmospheric physicist, Edward Hulbert, in 1953. And he was the first person to realize that ozone was having a profound effect on the atmosphere and on the color of the atmosphere. He was actually flying sounding rockets into the atmosphere, donated by the Germans after the war, and looking at the brightness of the upper atmosphere sky. And he couldn't reconcile the brightness of the sky with the models that he was making using pure Rayleigh scattering. And he eventually twigged that this was ozone gas absorbing the light in the high atmosphere. And this makes the zenith sky at twilight very different from what it would appear, what it would look like if there were no ozone in the atmosphere. Now, this absorption produces this remarkable phenomenon called the blue hour. This nice little sketch here, I'm going to go through this the opposite way round. The person who drew this sketch drew a sunrise. I'll talk about a sunset. The sun is coming down here, and for the last hour or so before sunset, you get the golden hour, which you're all familiar with. Everything has a lovely golden light if the air is reasonably clear. But once the sun has sunk a few degrees below the horizon afterwards, you get what the artists for a long time have called the blue hour. This is where the light becomes extremely blue. And this extremely blue period is the result of having ozone in the atmosphere, absorbing the orange light. This is a picture I took of a sunset over the Mediterranean. This is just before the sun sets. I set my camera so the color balance doesn't change with time. So I took that picture just before sunset, and that picture was taken about half an hour after sunset when the sun had sunk below the air. It really is very, very blue. Certainly when you take the pictures with a camera, which you keep at the same color setting, it's happening at a time when your eye is adapting to dim lighting. And so you're transferring from your color vision, your cone vision in your eyes, to your rod vision, and your rod vision, for your rod vision, you're colorblind. So it often appears just deep gray to you, but in fact, if you photograph it, it's extremely blue. And there are a few animals on the planet who have to adapt to this very blue twilight. And this is an example of, I think, in fact, it's the only animal I can think of that does this. It's the reindeer that lives in the Arctic regions, where most of the year is twilight for the reindeer. It has to, in the winter, it has to spend about 10 hours a day under twilight. And it's very dim light. It has to look at predators and it has to find its food. And it's adapted this layer behind the retina of the eye. This is called the tapetum lucidum in the eye, behind the retina. The retina has been removed here. This gives it an extra pass through the retina of the deep blue twilight sky. And this is a significant evolutionary advantage for it. I think the person who has his thumb in the picture here is hopefully in the audience. Hi, Glenn. This is your bit. That's your finger. These are my colleagues at University College. This is the way I would model this. This blue spectrum at the bottom is the way the twilight really is with the ozone. If I remove the ozone from my model, we get the green curve above, and the gap between, this space between, is the light that's removed by ozone. And this is why I call it the elephant in the sky. It's removed a huge amount of orange and light from the sky and dramatically changed the color. Without this ozone absorption, the twilight sky at zenith would be a pale grayish yellow, and not the deep metallic blue that it is. I'll move very quickly now because I know we've lost a bit of time. Are we okay, Manuel? Can I just finish off now?
So it's 5 o'clock now. If you want to wrap up, I think that'd be good. Then we have a couple more, a little bit of time for questions.
I'll go very quickly through this. This is the phenomenon of shadowing. It's mostly pictures. If we look at an illuminated sky on the horizon under a big cloud, we can see the orange horizon, which is orange because of extinction of all the light coming through under the cloud. That path of extinction is protected by the cloud from the sunlight, and therefore you don't get the aerial perspective that you would get in a clear sky, which I've shown in this diagram here. You can see the blueness of the horizon, which we call aerial perspective. This is a lovely mixture of twilight and aerial perspective in one of the Chilean observatories. The other time when you can cast a shadow on the sky is during a total solar eclipse, when the moon casts a shadow on the sky, and you can see the extent of the shadow here. We're closer to the edge of the shadow on this side, and we're looking through the longest path through the shadow directly forward here, and you can see the way the sky is reddened by this long path through the shadowed atmosphere in a way that's not over here. So that's a nice product of shadows. This is the shadow on the coast of Chile when this eclipse was occurring. I was going to talk a little bit about exoplanets. I'll skip this. This is the analogy of an eclipsed moon. I'll just show this as a beautiful picture of an eclipse, a sequence through an eclipsed moon. It won an award this year for this photographer who very kindly let me use his pictures. This is the deep blood red of an eclipsed moon. As the moon comes out of eclipse, you have a short period when the light grazing the Earth is traveling high through the atmosphere, through the ozone layer, and that light is colored blue. And you can see that beautifully here before the moon becomes bright again. And I'll just finish very, very quickly with the slideshow. This is what happens when the sun goes down. This is a dark sky in Chile. You see the beautiful galactic center overhead. You see these wonderful reddish streaks in the sky. This is air glow. This is energy captured by the oxygen in the upper atmosphere during daytime, which it releases slowly during the nighttime to produce red and green colors. This is what it looks like from the space station. You can see this layer of air glow over the Nile Delta here. If you look from the ground, you see it actually changes from just after sunset to this green color later on in the night. This decays more quickly than the green. They're both coming from oxygen emission in the atmosphere. This is to emphasize that the light from aurorae are the same transitions in oxygen, but it's a quite different process. Particles from the atmosphere. This is pumped by light during the daytime. This is pumped by particles coming down the magnetic field in the atmosphere. And this is a lovely picture of the juxtaposition of the red and the green emissions. And we end up with a dark sky. This dark sky is about 60 million times fainter than a sky in full sunlight, but you can capture it beautifully on modern digital cameras. You might recognize Orion, the belt of Orion here, and the Magellanic Clouds here, and the galactic center overhead. Okay, well, I'm sorry, I'm a bit late. We had a few technical problems along the way, but there we are. I'll stop sharing now. Thanks for your forbearance, Manuel.
Thank you, Bob, for this really, really wonderful talk. Very, very impressive visuals as well. So we got a bunch of questions coming in. I think I'll just go through them until we sort of run out of subjective
Yeah.
time. We're already 5 minutes past the hour, but I think that's fine.
That, yeah.
People are still here.
Yeah.
So we got a question from Jamie Zeitzer, who's saying, there was recently reported 2 days ago in Science Advances that the ozone layer has increased in the past 20 years. Does that level of change that is being reported, does the level of change that is being reported lead to meaningful changes in the observable spectrum of visible light on Earth?
Well, that is actually a very interesting question. And the answer is, it has a relatively small effect. And that is the fact that when you have twilight, there's quite a large depth of ozone in the atmosphere. And you're in a region of absorption formation where it depends rather slowly on it depends rather weakly on the amount of ozone in the atmosphere. It will have an effect. If any of you are familiar with astronomical spectroscopy, you'll know that when you look at absorption lines in stellar atmospheres, when they're very weak, you get a linear dependence on the number of atoms in the atmosphere. When it becomes saturated, when the light becomes stronger, the way the strength changes with concentration is much slower. We call that the flat part of the curve of growth. So yes, it does have an effect on the twilight colours, but it's a relatively weak effect. And I suspect that it can be seen by carefully designed observations now, but you would have to look rather carefully.
One question from Christian Fankhauser, who's asking, why is the blue peak of LEDs so bad for wildlife? What sort of evidence is there?
Well, that's it's a very interesting question, and we don't really know the answer. I think there are many reports, there are many phenomena that are observed in animals of various kinds about the effects of blue light on both vision and general well-being. The actual process by which this occurs is a very active topic of research at the moment. In fact, I'm working on this with my colleagues at UCL, but there are many people working on this. But it seems that blue light at around the wavelength of that blue peak in LEDs, the blue peak in LEDs comes about because it's a very efficient way of designing LEDs and redistributing energy to longer wavelengths. So there's a technological advantage in doing that way. But unfortunately, it has effects, as you, Manuel, will know better than I, on circadian rhythms and so on. But it also seems to have physiological effects. It seems that it can induce hypoxia in animals when they're over-illuminated by blue light of that particular wavelength. It gets absorbed by hemoglobin and myoglobin in the body, and it seems to interfere with the production of energy in the body from mitochondria. But I can't go into more detail than that now. But it's an interesting question.
Great, thank you. We got one question from Luke Helwick. Can you talk some more about the steps you followed to generate the sequence of spectra for paths of different total air mass?
Yes, well, very, very briefly. I've tried to simplify it as much as I possibly can, as you see, and I've ended up with this tau e to the minus tau expression for understanding the colours. If you want to do this and understand the intensities as well, you're going to have to do so many integrals that the sheet of paper would look like a musical score, which is why I missed all that out. But basically what I've done, I have my extinction program, which calculates the extinction. That's just basically computing the strength of the Rayleigh, the strength of the aerosol scattering, and the strength of the ozone absorption for a particular amount of atmosphere, and then using the negative exponential. Then I multiply by the optical depth in order to produce the source. And so basically I just run that model so that the optical depth goes from 1 in the red to 1 in the blue, which means very different air masses, and compute those spectra over that range of air masses. I don't know if that's it's hard to explain it in detail in a few words without a diagram, but it's done in a way which reproduces the color pretty well. I can't reproduce the intensities with any kind of precision in that way. It's far too simple for that, but it's a relatively straightforward model to do. It just involves a few columns of numbers and a few exponentials, but it's not difficult to do.
That's great. One question from Christian Fankhauser again. Is the green flash at sunset a myth or real?
It's certainly real. Again, that's a very interesting and rather controversial question. The green flash is commonly explained by differential atmospheric refraction and mirage phenomenon as the sun is setting. So you get various kinds of refraction going on through the layered atmosphere at sunsets, where you can get temperature inversions and so on. And this can produce a little spectra of the edge of the sun as the sun sets or rises. And occasionally that little spectrum can be split off from the edge of the sun. So you get a green segment above the sun. That's quite commonly seen. The green flashes need something else. And my belief is that this is due to ozone, which removes much of the light between the red and the green and blue. So it removes a lot of the orange light, and it produces a spectral break in the spectrum that's coming from a very low setting sun. And I have something about this on my Flickr website, but I think it's the combination of the mirage-like differential refraction with color in a setting sun, and the fact that ozone is creating something of a spectral break in the spectrum, which allows the red to be separated from the green. It's a very interesting phenomenon. It's quite complicated, and I wouldn't say it's terribly well understood yet, but that's what it's all about.
Great. We've got one question from Nan Wang. They want to know, recently I'm working on spectral changes of solar irradiation under different skies. I'd like to know the changing factors that influence the spectra. What else besides ozone level, which you mentioned? Can you suggest some keywords?
Yes, the keywords, I've ignored many of the absorptions that actually exist in the visible spectrum. Some of those absorptions can get quite strong when the sun is very low in the sky. These absorptions are called telluric absorptions. The strong ones are water vapor, molecular oxygen, and also there's another thing which is actually very interesting. This is the result of collisions between two oxygen molecules. You have one double oxygen molecule and another, and when they come close, during the period that they're close together, they become what we call four oxygens, quad oxygen or whatever, I can't remember the name it's called now, but the four oxygen atoms together, which change the spectrum of molecular oxygen a bit and induce absorptions at somewhat shorter wavelengths. So you get absorptions in the yellow, which are actually visible very easily with a visible spectroscope, just looking at the sunset sky. And there are also some absorptions even further in the blue. They don't have a very profound effect on color. They can be very strong in thunderclouds, where you get light scattered around a lot in very dense atmosphere. But these collisionally induced absorptions, as they're called, are very interesting for us because they sample the low atmosphere. Because you need two oxygen atoms to produce these absorptions, the strength depends on pressure squared or density squared rather than going linearly with the density and pressure. And so they're very sensitive to the conditions in the lower atmosphere. And we're very interested in this for extrasolar planets.
Great, quite a comprehensive answer. We got two more questions. Charles Draper wants to know, is air glow a problem for astronomical imaging?
Yes, it is. It's particularly important in the near infrared. as well as the oxygen, which I talked about, which emit single line spectra in the red. There's one at 5577 angstroms, and there's one at 6300 and 6363 angstroms. I know them very well. They're individual emission lines, and they can generally be avoided by astronomers. Astronomers can just cut out that bit of the spectrum. They have to try and subtract them, but they cut them out of the spectrum. But when you get to slightly longer wavelengths, you get a lot of emission from the OH radical, and that produces many, many, many lines, and subtracting those lines is quite difficult. And there are many tricks that astronomers have developed for trying to get rid of those lines, but they are a real problem. So in the visible, the air glow is not so much of a problem. In the near infrared, especially because they're so variable, it is quite a problem.
Great. And then we got one final question from Michael Herf, who wants to know, do you have a favorite empirical computational sky model? For example, Hozak-Wilkie is considered good for computer graphics.
I don't have one myself. I know that the graphic artists I've worked with extensively in ESO in Munich use these sky models for their astronomical graphics, and they would be able to tell you better than I would. I know there are a number of real physical models of trying to predict the color of the atmosphere, which are relatively successful, but they're very complicated. They're much more complicated than my model. So no, I don't use any of these models. I'm really, my ethics, since this is a kind of hobby of mine, I'm interested in understanding how things work. I don't necessarily want to go to the nth degree of detail, so I don't work with these very complex models. I just produce the simple ones myself. So I'm sorry, I can't really answer that question, but I know people do use them.
Great. We have, because we're almost at the end of the question list, one final question that just came in from Ruben Pastilla. You've mentioned polarization. Could you explore a bit more how polarization changes in daylight and what's interesting about it?
Well, the interesting thing is, because the way the scattering works, let's consider Rayleigh scattering for the moment. We have light photon coming towards a molecule of nitrogen, say, nitrogen 2. As the photon gets close to the nitrogen, the oscillating electric field in the photon will induce an oscillation of the charge in the photon. So the charge in the photon will, the charge in the molecule will start vibrating. The molecule will have a vibrating polarization. And that will act like a dipole antenna, and that will re-radiate light as a result of that vibration along a line. So it will radiate polarized light. So if you look at right angles to sunlight illuminating the atmosphere, so if you have a rising sun, say 10 degrees above the horizon, if you look 10 degrees down from the zenith, along the line going through the zenith, you'll find that the blue sky is darker than anywhere else in the sky, but it's also very strongly polarized. And the only reason that stops it being 100% polarized is that you get some aerosol scattering as well, and that dilutes the polarization a bit. So in a really clear blue sky at high altitude, the equatorial band with respect to the sun around the Earth's atmosphere will be darker, and it'll be almost completely polarized. The polarization pattern is actually more complicated than that, but that's the main element in the polarization of the atmosphere. And you can see this with the naked eye. There's a phenomenon, look it up, called Heidinger's brush, where your eye is actually sensitive to the polarization, the linear polarization state, and indeed also the circular polarization state of light entering it. So you can identify both linear and circular polarization with your naked eye. At least most people can, not all people. Depends on the structure of your eye.
Perfect. I think with that note, I think let's end the webinar. Thank you all for joining. And of course, a big thank you to Bob for presenting this really, really interesting presentation today, and for fielding all the various questions coming from various angles. So thank you, Bob.
It's been a pleasure. Thank you.